to Ivan Laptev. Ivan, are you here?
Yes, I'm here.
Okay. Иван Лаптев — это ведущий исследователь института ИНРИА из Франции, из Парижа. Это очень авторитетный институт. И Иван, он сам из России, да, но он будет делать лекцию на английском, потому что есть достаточно много терминов, которые не переводятся на русский язык в компьютерном зрении. Вот. И в целом, что хочется отметить, Иван также является организатором очень крутой конференции Machine Can See, которая вот-вот 8 июля прошла в Москве онлайн. И вы, кстати, можете посмотреть эти видео. Достаточно интересные лекции про понимание видео, про распознавание видеоизображений. Вот. И у самого Ивана очень много научных работ, которые опубликованы в ведущих научных журналах по тематике как раз компьютерного зрения, по распознаванию видео, по пониманию взаимодействия людей, по приложениям компьютерного зрения в робототехнике. Вот. И тема его лекции — это Scaling Visual Recognition with Less Supervision. Ну, дадим слово Ивану. Спасибо. Иван, пожалуйста.
Отлично, спасибо. Меня слышно?
Да, отлично слышно.
Хорошо. Спасибо за интро и спасибо за приглашение. Был бы рад приехать физически, но не получилось в этот раз, может быть, в следующий раз. Да, как сказали, что я буду делать лекции на английском, но задавайте вопросы можно на русском, постараюсь на русском тоже отвечать. И вопросы можно задавать по ходу дела, больше будет интерактива и неформальности. Окей. И также, да, если что-то непонятно, тоже перебивайте, спрашивайте. So I'll talk about visual recognition and in particular scaling visual recognition using less supervision. So I'll come to this shortly. I want to start with some intro. I'm sure you have a background, some of you have background in computer vision. You also had lectures in computer vision during this summer school. Still, I want to, just to get into context, I want to start with a few motivating examples. What is visual recognition? This is a slice of what people would like to do. For example, you want to label scenes, you want to understand actions of people, you want to recognize objects, and so on. And so this video actually was done by me manually about 15 years ago. And I had no idea that most of these things could be done automatically in a span of 5-10 years. So we didn't redo this video, but I'm sure that most of this can be done automatically now. Maybe not the kidnapping part, which is still quite high level, but actually understanding these scenes, which seemed very challenging 15 years ago, now it is much less challenging. So why is it difficult? Okay, as you can imagine, so computers don't see as we see, so they see array of numbers. And yeah, how to interpret these numbers is not obvious. So I want to, yeah, okay. So we have, why is it relevant? Why so many people are interested in vision? Because there's lots of video data and image data available. So you have a few sources, both archival and just the camera streams, and there should be mobile phones included, of course. And of course, there are plenty of applications, such as augmented to virtual reality, where you want to put the content into, or merge the content, virtual content with the real content. If you want to search, organize your video image collections. Robotics is a very large application yet to come. So currently robots are doing very good in say producing cars, but all what they do there is they just repeat the same operation all the time, so they basically have no sensing. So if we can integrate robots with sensing, and vision is obviously one of the most important sense modalities, we hopefully will be able to see robots in our homes soon, and autonomous driving, so this is coming. Right, so yeah, vision is hard. It was not obvious that it's hard. Well, one can imagine it's hard, but how hard it is, it was not clear. So it was started as a sort of master project in MIT about in 60s. And so people, of course, if you start with vision, so the neural network with 60 million parameters is not the first thing which comes to mind. So you start simple, and so you also start to explore the problem. So that's what people did in the 60s. And they more and more realized that there are lots of challenges. And this is not obvious because well, as we are seeing the world seamless without much effort, as we think. So well, the problems are not obvious. So it took some time to understand them, and so the progress slowly picked up. So in the 90s, in some industrial vision, one could analyze in the factories. Basically, it was already operationalized in factories, but not for consumers. Research was going towards object recognition, early stages. In 2000, around 2000, the first consumer applications came up, like face detection for consumer cameras. Maybe was the first noticeable application of computer vision which came to people. And right, so what happened in research over the years? So here's just one again slice of performance over the years, particular for object detection in the Pascal dataset, which was a landmark for many years of measuring visual recognition. So it had 20 object classes, and one had to write programs which would detect objects. So here you see that was some progress. It was stagnating, and then suddenly something happened in about 2012, 2013. Right, and that's so deep learning, you certainly heard of. So it's getting better and better, and for some tasks, like, so if you have a visual task, it's like object recognition or say face recognition, and if you really work on it and deploy some Buffy neural networks, it's likely that the machines will finally do it better than people. And so for face recognition, this is one of the problems which been in computer vision always, and currently the methods, they work actually better than people. Right, and well, another pleasant thing with computer vision is that it is about images and videos. So when you have nice results, you can show them, and if they're good, people will be impressed. So this is a detection that already 4 years ago detector which runs real time, detects lots of different objects. So here's another example of human pose estimation, which was a quite old problem in computer vision, which was considered as very hard, and here current methods solve it very well. At least, so this is 2D pose estimation in challenging scenes. Of course, you can imagine now people go for 3D pose estimation, maybe modeling the 3D body, including clothes. So of course, it's not this doesn't mean that we are at the end of the computer vision again. Like even like object detection here, if you want to do autonomous car driving creations system, obviously detection is important, but that's not the end. There are lots of things to do, like getting precision to false positive rate to really low values, or going to analyzing scenes in 3D and so on. Yes, lots of progress. Right, so let's see what actually contributed to this progress, and try to derive where to go next. So here is a neural network which has been shown millions and millions of times. So it's from the paper which made the breakthrough in computer vision, AlexNet architecture from their NeRIPS paper from 2012. And yeah, I think some people mentioned this before already in this summer school. So the neural network is not much different from people knew 10, 20 years ago. Of course, it's larger, and because it's larger, so it could process lots of data. And it also consumed more computing power than before. So that these are data and raw data and the computing power are obvious ingredients which made the breakthrough possible. Some people believed in it, but even they didn't know when this breakthrough will happen. And at some point it happened. But what's also very important, and that will be the topic of today's lecture actually, is that data, raw data and computing power is not everything. So currently, most of the methods which work well, they are supervised. It means that in addition to raw data and computing power, you also need someone to annotate images or videos. And now if one thinks of how to make the next progress, here are 4 ingredients: raw data, the network, the computing power, and the image annotation. Of course, all of these are important. So I would argue that maybe the image annotation is the main bottleneck. Of course, there's lots of development and understanding of the network architectures. We don't know because these are highly nonlinear models. The classical mathematical tools of analyzing them basically do not exist. People are trying to analyze or get a theory which will predict what new architecture will be better to train. So currently it's this topic is, it's giving something, but not as much as we want. Obviously important topic. Data. For some application, data is a problem, like in medicine. Data might be hard to find. If you want to analyze the standard images on internet, they are plentiful, or videos, so this is not a problem. GPUs used to be a problem. Now it becomes more and more accessible. Of course, people want to use more and more of them to train bigger models still, so you can get access to them. They're getting cheaper when the Bitcoin finally goes down. And the point, what really the topic of my lecture today is about image annotation. Why? Because image annotation or video annotation, if it's done manually, it's a real bottleneck. And it seems to be a stopper for progress. So we cannot just assume that we will have infinite manual labeling power, and we need to design methods which should cope with less annotation. So why? Because it's expensive. So say if you want to train object detector, so typically in a supervised manner, you have to annotate. Somebody has to annotate lots and lots of bounding boxes for not just for one object, but for all objects which you want to find. And even more than that, it's not that you just imagine that you want to annotate bounding boxes for 1,000 objects and train a detector. It's not that you just take 100 objects, 100 images with chairs, 100 images with tables, and annotate chairs in one subset, tables in another subset. You really need to annotate all objects, like complete annotation. You need to annotate all classes of objects in all images, and that's very hard. Another problem, ambiguity. So if you have a context, you can maybe say that this is a table, this is a desk, but labels do overlap. So if you're just given an image of something, it's all, and if your number of classes is 20, in Pascal, that's in most cases easy. But if you grow your number of classes to beyond 1,000, it becomes hard even to come up with a clear label for objects, and even worse for actions. So if someone asks you to label these actions, you may label them as running. If you see the full images, running is true, but maybe that's not the first label which will come up to your mind. It's not probably the most interesting labels for these images. So labeling is hard and ambiguous, and that's why in this lecture we are going to talk about how to avoid manual supervision and still train good models for visual recognition. So that ends my intro. Yeah, if you have any questions, again, please ask if you have a possibility. Right, so so basically what I'm going to do now, I'm going to talk about few papers which we've done over the last, say, 5-6 years, which address this subject. And the first one is actually this came out quite after, well, just 1-2 years after the NeurIPS 12 paper on AlexNet. So we were exploring the neural networks. We were very surprised how well they work. So soon the obvious question came up, like if you want to train it for many things, like how can you avoid annotation? And here the setup, okay, I'll come to the setup. So say the problem is object detection, and typically it is addressed, as I said before, that you need someone to annotate bounding boxes around objects. Right? So if you want to detect chairs, someone has to annotate all chairs in the image, all tables, and the scenes should be realistic. Flat Earth is here. Okay, one straightforward way to do object detection, that's what people tried in the beginning, is to pre-train neural network on some large data corpus where you have lots of labels, image level labels, and then fine-tune it on something else, on your target problem. And so that's what we tried, and that kind of worked. So if you have a ground truth bounding boxes, you can crop the images, you can extract features from these crops, okay, and then you have for each crop you have label, and you fine-tune your network. Right. So what's fine-tuning means is that you keep the pre-trained layers fixed, and then you backprop only through a few first layers, or maybe you backprop through everything, but you make the learning rate a bit smaller for the full network. So in this case, we just fix the previous layers. Depends on the number of data you have. So if you don't have enough data, you don't want to fine-tune a huge network because it will overfit. Right. So so the question is, are bounding boxes really needed if you want to do object detection? So if we could avoid bounding boxes at the training for object detection, we could scale it up to many object classes. So that would be great. Of course, if you like, unsupervised learning is questionable. At least you want to align your network to your target task. So if you want to detect bicycle somehow, you need to say network that what is a bicycle. And the idea here is to try to use, it's not a new idea, so the idea has been around for a while, is to use information which is already available, which somebody provided probably for different tasks. For example, when people upload images to internet, they often also describe it with a few words or a few sentences. And hopefully, if you get all this data, hopefully, because the text is correlated with images, we'll be able to capture this correlation and at the end associate it with some words with corresponding objects in the image. So it's not completely unsupervised, but we are not asking anyone on Mechanical Turk anywhere to annotate the images. And there are really plenty of images. Of course, if you call these annotations public bikes in Warsaw during night, they are noisy. So bicycles are mentioned, but they may not be mentioned in some images. Also, there is no spatial correspondence. We don't know where the bicycles are. That's the problem we try to solve. So here's the setup for this paper list. That so during training, so you want to use so-called image level labels. So we don't want to have bounding boxes. We just assume that someone provided annotation on the image level. Right? So for this image, the annotation would be there is a person, there is a chair, but there is no airplane, and could be also actions, doesn't have to be just object, could be anything. It could be about scenes. The person is reading, but there is no bike riding, there is no running here. And at test time, we would like to not just say that these images contain a person elephant, but also say where the person is, where the elephant is, or where the reading is happening. Right, so that's set up. So that's what we call weekly supervised learning, where we, at the training, we have less input than what we want to have at the test time. So let's see how this can be done. Actually, the modification which we had to do for the network, or in this paper, was quite minor, but it gave quite interesting results. So basically here you have the, I hope you see my mouse. So here you have the standard neural network, was AlexNet at the time. And then, so it usually ends up with the one neuron per class, with one output per class. And how you get these class outputs, you usually average pool or max pool the feature maps from the previous layer. So what the modification which we made is that we first avoided the spatial max pooling. Sorry, we avoided the, for each location of the image, we have provided a score per class. And then, so these are not feature maps anymore. And then for each score map per class, we did a spatial max pooling. So basically taking, so if this is a score map for a particular class, so we take, we do max pooling, let's say here, and then we apply standard loss to just to this particular location, then we break prop to this particular location. So this works actually surprisingly well. And so here is intuition why it works and what it does. So imagine that we have image level labels. So for this image, we have airplane, but no, we know that there is no car, there is no chair, right? And so let's say here is our, during training, we can observe the score map for a particular class, for example, airplane. And right, and so our network believes that the airplane is here. So what it will do, it will just trust itself, and it will, because we know that the airplane is there. So we have airplane image level label airplane. So the loss will give a positive gradient, so it will reinforce the. It will be even more confident after updating the weights. It will be even more confident that indeed the airplane is here. So negative examples are very important. So it's not that you only know that there is airplane here, you also know that there is no car. So you can imagine why the network may think that this is a car, because it sees the wheel. It has seen many cars with wheels. So it just for the moment, for some epoch of training, it thinks that this is the wheel and it must be car. So that's why it gives it high response here. So what now happens, that because we know there is no car, so the network will give a negative gradient. So it will try to decrease the confidence that the car is here, okay, this location. So it will suppress this maximum. And you can imagine now that if it, over time, over training, so it gets this way, it reinforces the correct maxima and it tries to suppress the long ones. So here is a visualization of score map for motorbike over training time. So on top you see the training iteration, probably thousands of images, you know, or maybe epochs. So what you see, I'll play it again. So first network doesn't know much, and then it starts to fire spatially at locations where the motorbikes are. Also, interestingly, so for typical views of motorbikes, it locates its pretty soon during training, while for more unusual views of motorbikes, like in this image or in this image, so it takes more time for the network to understand where the object is. So here it's already localized, here it only comes later. So that's basically just observing what the network is doing, but this what it's doing seems very intuitive. And results also look intuitive. So here, what crosses are drawn basically when over taking the spatial maxima over each score map, and for each object class producing one cross where the network believes the object is most likely. So it works for many different objects. It even pretty well localizes small objects in an image. Like the kite is quite small. Sometimes it fails, but the failures are also explainable. For example, here, the baseball glove, it does fail, but it's still quite close to the correct location. Sometimes it's, the failure is also interesting in terms of mislabeling. So the network thinks this is a bench, and one can speculate, but I would imagine it doesn't think it's a bench because of maybe of the structure itself. It just sees the person and assumes that if it sits on something which looks not far from bench, it should be bench. All right, so I think I should speed up because I have a few more things to talk about. So actually, okay, so still the same method, just trained for actions in still images here. So we want to recognize, from still images, we want to recognize if the person is playing instrument or reading or jumping. And well, so it's the same algorithm. So the network has never seen actually where is locations during training. The network has not been told where the jumping person is. So, but it does figure out it completely automatically. So why it does just one person is because we just take one maxima. Imagine if it would we take multiple maxima in the image, so it will also detect this person. Right. Again, some funny mistakes, which are also quite intuitive. Here's a pizza box, and the network thinks it's a using computer. Right. So let's me now switch to video. So video is a subject we are working quite a lot, and still the goal, the overall goal is within the topic of this lecture. So you want to analyze video and want to recognize the video content without asking people to label it. And for video, the labeling problem is even more important than for images, because labeling videos is really hard to watch for. If you want many examples, you need someone to watch for thousands and thousands of hours. So the trick which we tried in this paper is to use movies and movie scripts. And movie scripts, if you don't know, these are not subtitles. They include the speech of people, transcribed speech, but they also explain what happens in the scene, why they exist. It could be shooting script before or after the movie was produced, or it may be some people who are just interested in movie or TV series who transcribe what happens. So here's a scene. Is a quite detailed description. Of course, it doesn't describe everything, but it has names of people, it has actions, has scenes, and so on. So what's missing is that we don't know the correspondence. Say head waiter. Who is the head waiter here? Where is Isa? And what does it mean to sit? Who is sitting in the scene? So this information is missing. And in this sense, it's similar to just the problem I described before, that you have some relation between text and images or video, but you're missing spatial correspondence. And here in video, of course, you're missing also temporal correspondence, because this part of text may be written for, say, a range of 20 seconds, and you have video and sequences of events, so you need both temporal and spatial correspondence to be resolved during training. And that's what the method is trying to do. Well, there's some technicalities just because scripts don't come with time information, so there are some tricks to propagate rough time information from subtitles. And so now I want to shortly talk about some details of the method, which tries to resolve names of characters and their actions from scripts and videos. Right? So we don't want to annotate who is Rick, who walks, but we want to learn and localize people with their names and actions. Right. So, so I'll try to explain a bit of math here. So what happens? So this is a standard loss, supervised loss. It could be for neural network, could be for SVM. So in here, in this work actually was still SVM, and it's a linear. Basically, it's a linear classifier. So what Z is? These are labels. W and B. This is a linear classifier, and X is the data, and 5X are the features. Okay, so for example, if our problem is to name people in movies, we want to automatically say who is who in a movie without using an annotation, just using scripts. Right, so we can write this loss. Now, if Z would be given, this would be a standard, and you can also, here is a square loss. If you change this to hinge loss, this would be standard SVM. So this would be standard supervised learning problem with a linear classifier. Of course, features usually not linear, so then it's not linear, but we are just learning the linear part of it. Now, the problem is that we don't want any manual labels. It means that we don't know Z. And if you try to solve this loss both for Z and for W, you minimize this thing. If you try to solve it both for Z and W, you can easily get trivial solutions. For example, you put everything to 0, the loss is happy, but you get nothing out of it. So that would be a completely unsupervised learning. That's why unsupervised learning is hard. But we are not in a completely unsupervised setup. We do have scripts, and the question is, how can we construct a model that use information with scripts? And that's exactly what's interesting on this slide. To understand, so just describe quickly what's this, the structure of this Z matrix is. So it has rows and columns with labels. And the columns correspond to different characters. We assume we know the movie has 20 characters from the cast, and so say we will have 20, maybe 21 column, because there will be one column for unknown people. And then the rows of this matrix, they correspond to person tracks. So we assume we have a face detector and it's face tracker, and then each row of this matrix will correspond to one track which we detected in the video. Now, most important, the following is that if the script says that for some period of time, say 10 seconds, that Rick is walking, for example, then we can assume that this piece of video contains Rick. So we know that at least one of these tracks, which happens inside this 10 seconds period, it should be Rick. Okay, what it means that one of these Z's in the intersection of the Rick column and all the tracks which happen during our 10-second intervals, hopefully should be, at least one of them should be Rick. It's not sure, maybe the script mentions Rick, but Rick does not appear on the scene. So the annotation is noisy, but we can make such an assumption and see what it gives. So hopefully, if assumption is not completely wrong, it will be, it will help us, and it will prevent the minimization of this loss going to trivial solution. So at the end, what it is, how to solve this? We have this loss. We have it's a square loss, so the values of z are not 0, 1, so they are real values. Otherwise, it will be hard to make discrete problems are hard to minimize. So right, so we can write this loss with the real values and minimize this, but under constraint, which is here. So which basically implements the intuition that if one of these tracks include RIP, then we can write it as a sum of all these values should be greater than 1. And basically this is it. You can do the same for actions and so on. So yeah, I just want to jump to, okay, there are some details, more details in the paper, how to do it not just for one movie, but do it for many, many movies. Just want to show results, how it works. So here is a result of just naming phases by minimizing the loss, which I just described before. And it's again done without any manual intervention. So there's a phase detector and phase tracker, which is run on the video. And then, yeah, so we, for each track, yeah, we construct the Z matrix with tracks and then minimize the loss. And then the algorithm automatically figures out who is who in the video. So it can associate names of people with faces automatically. And right, and the same thing happens for video. I hope the video plays well. So here are results where we at the same time recognize characters, so name people, and also recognize their actions. And that's already quite work which was done quite sometimes. I'm sure nowadays with more better descriptors one can get even better results. Right, and okay, that's also an interesting curve that the more data we add, the better performance becomes. So here's for actions. So on x-axis, you see if we train on 30 movies, on 60 movies, we can get quite a bit of gap. So usually, okay, these curves usually look like saturating, but if you plot them in log scale, they are showing linear performance. So it means that to double the accuracy, on a logarithmic scale, you will need to double the number of your data. So so this is interesting. And okay, so some summary so far. So what good things we could show is that, so we've shown two things. One is that we can localize objects without providing bounding boxes or localization information during training. And so similarly, we can locate and recognize actions and characters without providing this location information at the training time. So one thing which I didn't highlight, but in all these methods which I described, the features, they were fixed. So either they were pre-trained on ImageNet, like for images, or they were pre-trained or even handcrafted for the action localization. And that's something which is not optimal. So I believe that if we optimize the neural network for the task, not just a few layers, but the full network. So if you do end-to-end, what is called end-to-end learning, this should be better. However, really to do end-to-end learning of millions and millions of parameters in network, we need more data. Movies are great. So here were 60 movies. 60 movies would be maybe 90 hours of video. Turns out this is not enough for train modern neural networks, so we need more data. So in the next few papers which I'll describe, they're going to be about how to scale up, and here means scale in terms of more data. So we are still in the video. We want to better analyze videos, and we are searching for data which will come with some automatic metadata, and where we would not need to which we will not need to manually annotate and get improvements in final recognition or localization. Right. So here is one interesting resource called WikiHow. Some of you may have looked at it. So it has lots of different tasks. Here are just a few examples of them. Many of them are not visual, non-visual, so like how to be healthy, or how to April Fool your girlfriend. Crawling this site for tasks is easy. So you get about, if you just text crawl it, so you get about 130,000 of different tasks described in this website. Okay, so there are no videos. Well, sometimes maybe there are videos, images, but that's not what we are using. So we just, for now, we just want to get names of tasks, and not all tasks, but better to have visual tasks if you want to learn visual models. So therefore, so there is a manual step in this process, but this is the only one. It's not very expensive. So it maybe takes a few people a few days to go through this 130,000 tasks. Go through means just read the names of these tasks and subjectively discard some of them which do not look like they could be recognized from vision. Okay, so and then the last step is to just go to YouTube or any video search engine, automatically search for, say, how to sew an harpoon or how to break a chain, and download all the videos, or maybe a top 100, top 200 top videos which will come up. So the data is actually interesting. So if you type in YouTube how to change a car tire, so this is a typical video which you get. So it's someone who uploaded it online for other people to know how to change a car tire. And it's not just that this video showing how to do it. The person also describes how it does, and it describes while the person is doing this. And it's not just one. You will not find just one example. Actually, you will find for many tasks, you will find tens and even hundreds of different scenes where people show how to change the car tire. So this is great. Another important point here is that what I already said, videos are narrated, and in recent years, automatic speech recognition became very, very good, and YouTube provides nice captions. So what you see here is actually, I think it's automatic speech transcription. If it's okay, maybe it was curated by us in this video, but automatic speech transcription is quite good. I'm sure you've seen it before. So what we get basically, as similar to movies now, we get a setup where we have videos and we have descriptions of these videos, but at a much larger scale. So it's not 90 hours, it's much, much larger. And that's the scale. So this is the data set we created. Automatically means without doing any visual annotation. So we did a bit of text annotation for WikiHow tasks, but then we did not touch any pixel or annotated any video. So it's called How 200M. Why? Because it's based on, so we crawled 1.2 million of YouTube videos based on the names of the tasks, and then chopped it into short clips which corresponded to short text segments. And that's provided 136 millions of short video clips with corresponding captions. So the length of these clips typically would be like 10, 20 seconds. All right, hope it's clear. And so what it gives that the data set is actually 1,000 times larger compared to similar data sets which existed at that time, just 2 years ago. So the existing data set, they had videos and corresponding descriptions, but they were manually created. And creating manually 100 million short clips, annotating manually 100 million short clips, this is would be a huge effort, and that's why previous data sets, they were very small. So our data set is much larger, but it's also much more noisy, of course, because there are mistakes in these data sets, but the 100 to 100, how to 100M has, of course, many more mistakes because there is no guarantee that the video is aligned with the text or the person is talking about, actually about the video, maybe the person is talking about something else. Yet, so there are lots of, in this data, lots of diversity, lots of examples where people describe very different tasks like so cutting wood or, yeah. So it's instructional videos. So because we are departing from the how-to website, so most of these videos are instructions, how to do things, or vlogs, and so on. So it's a bit of specific data, still it's very diverse. And so what I want to describe a bit now is the algorithm which we developed for this data, to train from this data. And just remember, so we already had we already have methods which we could train. If we have pre-trained features, we could train them from video and text. So here we want to learn the full representation. So what is the task? What is the loss actually? So the loss is going to be a bit different here. Because so if the previous work I described, so we were still relying on the labels. So here we don't want to have any labels. We just want to learn from raw text and from raw videos. So what the method is doing is it extracts some features with a neural network from the video. So I didn't talk about how to extract features from the video. Just believe me that there are neural networks which take a small piece of video, say, I don't know, 16 frames, 32 frames, and either just treat it frame by frame, extracting features, and then averaging a feature vector. That would be very simple. Or a bit more sophisticated is to have a 3D convolutional neural network, which will slide filters over space and time, and this way will capture more temporal evolution in the video. So I'm skipping this part. There is, of course, lots of literature in this. So we assume that just we are using one of these networks, and important is that they can be trained end-to-end. Right, so these are video features, and in text, similarly, so you can, text nowadays is also processed with neural networks. You can just take a sentence or a chunk of text, put a neural network, and get a feature vector out of it. Right? So that's why, and now the problem we want to address, one of the problems we want to address is to, well, the problem we want to address actually is to train a good visual representation. What is good is, you can define it in many ways, but practically you need some loss which will tell which is a good representation, which is a bad representation. So you need at least one proxy task to learn it. And the proxy task here, which is actually also not just proxy task, it's a real task, is to try to get the corresponding visual representation and text representation to be close in the feature space. Right? So for this purpose, of course, the dimension of features, so if you take a 1 second video on the top and corresponding text at the bottom, so we want them to match to, each of them matches to produces a feature vector of the same size and if they correspond, we want them to be close. Right? So say this sphere, so imagine these features are to normalize, so they lie on the sphere. So you want to features of corresponding text and video to be close to each other. Right? Why? What can you do with this? Well, if this would be interactive, I would ask you a question, and hope to get an answer. Well, I will answer myself. So you can imagine now if you have lots and lots of videos, let's say distributed on this sphere. So you have a data set of millions of different videos, and now you want to search this large database by text. So if you have this aligned text-video representation, it becomes very easy because you just encode your text with a network. You put it, well, and then you do nearest neighbor on the sphere. So you just compute distance to all the videos, and then take the nearest neighbor, and that's it. And that's actually, well, this is a text-based video retrieval. One of the tasks we consider here in the paper. But okay, there are maybe more tasks, and what I will show just in a second, which will use the same representation, but we learn this representation on the task of text to video matching. Okay, I hope it's clear. Now, it's not that easy, so you can do this, just assume that you have a correspondence between text and video and train it. It doesn't produce that great results, and here's why. Because if you just take a video and take the, you assume you have a temporal alignment of speech to the video, and you just take the most close, well, in time, right? So this text, well, you know, person is speaking, so at a particular moment, this video happens in the same moment. So we just assume that they should correspond. But they may in fact not correspond because well, the person may be talking for a while. Here, the speech is about herbs, you know, some oregano actually doesn't happen in the video. So here is a spinach, and the person is tosses spinach, so there is no oregano here. So if we learn the correspondence between oregano and this video, it actually will be wrong. How to address this? Well, maybe we should not just assume that there is a one-to-one correspondence. Maybe we should relax assumption and say that hopefully in a longer time interval around this video, so say maybe this video is 3 seconds, but if you look at the text, basically the speech, maybe a plus minus 20 seconds, hopefully one of these descriptions, not the one which happens at the same time, but maybe before or after this video, maybe they will be correct. And that's the main intuition behind the method in this paper, that we want during training, want to figure out which descriptions do correspond to the video and which descriptions don't. And so that can be implemented with these laws, which looks complicated. Actually, it's not much complicated. It's more or less the same multiple instance learning problem as we looked at before, the paper I described before. So, so what's important here is that we have positive and negative pairs, and then we try. So we try to maximize the positive and minimize negative. So what are the positive pairs? So positive pairs would be all the positive candidates. Positive candidates will be all the text and videos which are roughly appearing at the same time. Go back here. So like all of these would be positive pairs, okay, for now. And what's are negative pairs? Negative pairs are all the, say, captions and some other videos. That's very, very easy to construct. And now, so because of this sum, so you do sum over the positive positive videos here, so that this sum implements this multiple instance learning that we assume that at least one of these positives should be correct, and so then it's maximized. Right, and so this is the loss, and now the neural network is very straightforward. So it's a 3D convolutional neural network which operates on 32 frames input. So you chop a video into 32 frames chunks, extract the feature with a network, and so, for example, reduce it to a 512 dimension. And there is a quite standard neural network for text, which at the end also produces that feature of the same dimension. And that's it. So you take lots of data, actually the 100M data, and you train on it. And then what's good about it is that you train it for text to video retrieval task, but you also train the video representation. And this video representation you can, as people use for ImageNet video image representation for other tasks. So here you can use pre-trained video representation for other tasks, such as action localization or action recognition, and so on, and see how it performs. Right, so here are some interesting results on video retrieval task. So here is a network which was pre-trained on ImageNet and kinetics. Kinetics is both are, so ImageNet is still image dataset, annotated. And kinetics is a video dataset, also manually annotated. Now, so if we see what, if we train on our data, and actually only on our data, so the last column here is we train only on 100M, which was not manually annotated. So we actually get better results than if you trained on label data. And that's interesting. That's before it has not used to be the case that weakly supervised methods, they've been around for a while, but usually they performed worse than fully supervised method. Here, probably because we are looking at video, and getting a video annotation is really hard. So large scale fully annotated video data sets don't exist. So here, even with very noisy annotation in how 200M, we are able to outperform methods which are trained with available fully annotated data. And similar things observed for not just for text to video retrieval, we also observe it for other tasks such as action recognition or action localization. So the method does perform very well. Here is a qualitative example of text to video retrieval. Actually, there is a demo online. You can look at it, and not only look, you can search, for example, for cut red pepper. So it will find the videos of what you search for. You cannot search for anything because if the video corresponding to description is not in the data set, of course, it cannot be found. But what this shows, it does find quite fine-grained things. For example, there was the warp samosa. Samosa is some Indian food, and well, it's not just one example. It's really it can find very fine-grained things like, say, cutting paper in circle. So it will find very specific things. So it does train very well. Again, they want to stress that this has been done without any manual supervision. So it was lots of video download, lots of processing. Like training these networks is hard. We have to send our student to DeepMind to use Google infrastructure to train the networks, but yeah, with lots of data and infrastructure, results are pretty good. And It's also, so you don't, okay, it's, you need lots of infrastructure to train the representation, but once representation is there, you can use it for many other things. And by the way, yeah, the network, the pre-trained networks and the code, I think the code also provided on our website, so you're welcome to use it. All right. So switching to another work, which is also the same spirit of using large-scale data for now for a bit different task. Lots of videos for different tasks, and the task here is to learn a system to automatically answer questions about video. So there is a related tasks you may know of, automatically answering questions about images or automatically answering questions just in text. So this is one of the standard tasks in text natural language understanding. So here is answering automatic learning system to automatically answer questions about videos. Example, the question is where are the men? The correct answer is on track, and yeah. So that would be the open-ended question. So you just ask it. You ask. The system is asked the question, and then it has to produce any text, or it could be posed as a multiple choice question answering. So given this video and the question, where are the men? There might be 3 proposals: running, talking, shaving, and the network has to pick the correct one. So the first one is more difficult, and that's what we are addressing in this paper. So obviously, you can imagine lots of different questions and lots of different answers, lots of different videos. So if you train it on small data, it won't be good. So you need lots of data, and lots of course, variable data from different domains. And so if you want to have lots of data, annotation of manual annotation will be prohibitive, so that's not going to work to train good system. So here are a few examples, more examples of questions, maybe more simple, like what color of the dog. This could be answered even from a 1 frame, but then if the question is how many times does the cat leak in this video, so 1 frame obviously is not enough. We need to do a video understanding. All right, so here's the overview of the method. And so overall idea, I will explain in the next few slides, is to automatically, given data and narrated videos, to automatically generate question answers and to learn the video question answering system from automatically generated data. All right, so let's go step by step. So first, what kind of data? We are still using this How to 100M, with 130 million of narrated videos, which are very noisy, but there are lots of them, so we hope to get the useful signals. However, so this data was quite suitable for matching text to video, as I explained before, but now our task is to solve the question answering. So in this data, there are narrations, but there are no questions and no answers. So how can we use this data to for this task, to train the model for this task? So that's the question, and here's the solution, at least one of them. First, we just use already available methods for text answer and question generations. So no vision here at all, so just a pure NLP. So in NLP, people have already trained, probably in a supervised way, trained networks, which given a text can produce reasonable questions and answers. Okay? You assume that this network is just given. All right, and now we want to do it not in text, we want to generate data for video. So what happens, we have a narrated video on the left. Narrations are noisy, so we use some some block for a sentence. So it's split in the sentence usually splits. We have some sentence extractor, basically automatic punctuator method applied. It works a bit better with it. But then the main point is that given the sentence, we now can apply an answer network. So say I put up some pictures of him with another monkey. So this is a sentence, and we have a network which can generate the answer. Say it's monkey. Okay, so it just generated pure from text, it just generated an answer. And then we take a network, which another network, also pure text-based network, which, given the sentence and the answer monkey, it will generate the question. So what animal did I put up pictures of him with? Maybe not the best question and answer, but it's completely automatic. We didn't have to do anything with it, so we just need to apply the pre-trained network. And so why is it useful and how does it relate to vision? Well, because we have now paired, aligned video. Now these sentences are aligned with the video, so we cannot, if we assume that this sentence describes the part of the video, we can assume that the generated question and the generated answer correspond to this video. Right? So if you show somebody this video and answer and put these questions, so the person should be likely to answer this answer. All right, so I hope this is clear. So, okay, here's one more example what the method will do, say for this video and the input speech. So here somebody talks about cutting, and the automatically generated question will be what do we do at the bottom, and answer would be cut it off. Not always so good. So here is a incorrectly generated QA pair. Why? So it generates the what color did you peel on the other side? Okay, so this question doesn't make quite sense. So basically, it's an error of the question generation network, which is a pure text based network. And sometimes the visual content or the text narrations may just not be descriptive for the visual content, and then okay, you get some garbage. Still, you get quite many good questions and good answers, and you hope that despite some noise in here, so we can train a good network. So training network is quite straightforward. So we have a text encoding. Here is a bird model. We have a video, text and video, joint video and text encoding, which is a I think which is a transformer, cross attention transformer, and at the end we just want to match this representation and this answer. So we are encoding together question and the video, and we want to match it to the correct answer, similarly to as we did for text to video matching. Right? Just the difference here is that we, in addition to the video, we also encode the question. Right. Right. So here's a data set which is manually collected just for test purposes, so that we can battle with results. And right, some few comparisons. The last line is the method, which is our method. Works better compared to what? The first line is a method which only looks at the text, doesn't see the video. So you just pose a question, and it's not random because the answers are correlated with the questions. But okay, our method works much better. And then another baseline is to have just to train text video matching, as I showed before, without automatically generating video question answer pairs, and that's doesn't work. Okay, few qualitative results. What is man cutting pipe? What is the largest object at the right of the man? Wheelbarrow. What fruit is shown in the end? So that's quite tricky. It means that the method actually needs to understand what's the end of the video and pick up the correct objects, because there are multiple objects in this video. And the correct answers watermelon. Okay, few results. Comparison to state of the art. So this is actually on archive now. It's not an under submission. All right, I have two more. I have about 15 minutes and two more papers to talk about. So I hope I will have some time, and then also have some time for questions. So I've been talking about images and videos and how to scale it up by scaling up automatically generated, either automatically generated annotation or, so taking the automatically generated metadata, assuming it's somewhat correct, but also has lots of noise, and trying to learn from this data. So that's all good. There are also issues with computational issues, and the two last topics I will be now describing, they are more about computational issues. If you want, especially in the video, if you want to say do video retrieval, like text-based video retrieval, well, there are computational issues with training the models, but then even at test time, at the inference, if you want to search a huge database of videos, there are 4 images, so there are issues with this, and that's what I will talk here. Actually, yeah, the first thing will be about images. Images, videos, more or less the same for us here, because for both we extract features with some slightly different networks, but at the end we just represent them as features. All right. So let's assume we have a huge database of images, and we want to find an image where the dog is riding a bike on the street, right? Not very common image. So there could be 2 different approaches. So one is more standard, and that's what I described before. So you just have a separate encoding of vision modality and text modality, and then you do basically dot product. You compute the nearest neighbor between your. So if your query is text, and you have millions of images in a database, so you have pre-computed visual features for all the images. Okay, so they're just on the disk somewhere in your memory. Then you have a text query. You encode it as a feature vector. There's no problem with it. So this is pre-computed. This is basically 0 time. And then what we have to do, we have to do the nearest neighbor to all the million images. And that's quite easy because you just do dot product. So it's a matrix multiplication. You use GPU, it's optimized. So that's very fast. Right. Another way you could imagine is to take, say, a vision transformer or some other, maybe even convolutional network, and encode images and text earlier. Okay, so you put some. So here there are 2 streams, vision and text, and they're completely independent. So the only interaction happens here, and we hope that the features are learned in such a way that we will be able to find. However, this dot product is a very simple operation. So one can imagine that if we have more complex operation, which done both on visual and text modalities, hopefully it will be better. And actually, it is better. Like if you do nowadays, so transformers. Well, transformers have been very popular for text domain for a while. Since 1-2 years now, they're also becoming very popular in vision. And that makes the approach homogeneous. So we just treat images or videos and text inside this one transformer architecture. For example, doing cross-attention between images and text. And that means that we are actually performing lots of operation jointly on pixels and words. So this is great. You can get, you can train it to get better similarity scores, but there is an issue with performance because this operation takes lots of time. Right? Well, it doesn't take lots of time for one image text pair, but now if you have millions of images, so you have to actually run, and so you search for a text query room with 2 televisions. You now have to run this network millions of times at inference time. Right? So here just the dot product, here just you have to run the network millions of times. That's a huge difference. So this vision text transformer, joint encoding, okay, let's call it, yeah, this is dual encoder, this is vision text transformer. It works better than just doing the dot product. Right, so basically this is what I already described. So that's very fast. Yeah, I think I basically described all of it. So this is slow because you have to, for each image in a data set, you have to run the network. All right, so the question is how, so we have one slow network and one fast network. And slow is better, fast is a bit worse, but much faster, so can we somehow combine them? So that's the topic of this paper. All right, so this is a slow model. So the fast model, basically it's the same as I described before. We learned visual modality, text modality, and the pairwise loss to match them. For transformer, so we have a more complex maybe architecture, which does not produce just feature vector, it produces a feature vector with spatial resolution. Why is good? Because it will have more details. Right? And then we match it to text in a cross attention fashion. And then we have actually the loss here is a prediction loss. So we are predicting the text. Okay, I'm not going into details, so just of the losses there in the paper. Most important are 2 things, like how to merge these two networks. And so there are 2 tricks, and one is distillation. So you may have heard of distillation. Network distillation was introduced in 14. Now there are plenty of different methods, but the basic idea is that you have one or multiple neural teacher networks, which are complex, but they're producing good results, but they are slow. Now you have some small network, say called student network, and you want it to perform as good as teacher, but faster. So what one can do is here in this particular paper, so they both of them, they solve, say, classification problem, and you first train a teacher. Okay, you fix it, you don't train it anymore. And then when you train a student, you want the output of a student in terms of class probability to match the class probability of the teacher. Okay, that's the Kyle divergence here in the term, so that's the objective. So you don't train this student, you can train students with the labels as well, but okay, then it's not going to be good. What this paper shows, you train it also by matching the, not just labels, but also the class probability of the teacher actually becomes better. And you can do it, I imagine, on not just at the last level of scores, class scores, but you can also apply this idea on the earlier layers of network. Okay, so that's very quickly about distillation. I'm running out of time. The interesting point in this paper, like how, okay, you want to distill this transformer, complex transformer network into a dual encoder, but the standard distillation idea doesn't work here. Why? Because here you have one network, here actually are 2 networks. So how do you cannot, there are no classes, so how would you transfer the distribution from here to here? So that's not obvious, and here's the solution. So basically you have a dual encoder which computes the dot product and generates, so when you train a network in your batch, you always have positive, negative examples. And so for each pair of text and image, it produces some score, and this is the distribution. And for the same batch, you can apply vision text transformer, get the scores, and actually now you can try to you construct a loss which will minimize the chiral divergence between these two distributions. So that's one idea, one of the key ideas in this paper, which makes it work. And then re-ranking. Re-ranking is a standard idea where you first apply the fast method and then take the top, say, 100 responses, and then you apply the slow method to re-rank and get better results within. You won't get better, the ones which are beyond your threshold, beyond the 100 first examples, you won't retrieve, but these 100, the first 100 examples, they will be retrieved better. So in terms of numbers, so here's a, so if you want to evaluate the accuracy and the time of retrieval, so here's image retrieval, there are also video retrieval in the paper. So here's fast, here's slow, right? So it takes much longer, but it performs better. So if we do just distillation, well, we just run it's the same fast as fast, but better. So distillation really works. And then the re-ranking, it basically matches the slow. Right, and it becomes 100 times faster. Some comparison to state of the art. So that this paper was published in CVPR 21 this year. It means that it was done before November 20, and since then there are even better methods appear. So it's, the research is going very fast. I have almost no time. I wanted to just maybe mention the our last paper, which is on archive since June this year, and it's also about, so actually this is purely about vision transformers and how to make them more efficient. Okay, let's see if I can explain it in 3 minutes. Okay, references are here. If you're interested, just should look at these papers. These are quite hypey papers from last year, or from this year actually. So right, so you have well, transformers. So I think I won't have time to explain transformers in 2 minutes, but so important point with transformers is that they have n-square complexity. So the say if you have number of patches as input, the convolutional networks, they will treat it. The complexity is linear. In transformers, the complexity in both memory and computational is square, because you do you compute the pairwise terms for all-to-all patches. So that's the problem, and that's the problem we try to address here. So standard self-attention, that's where the square complexity come from, is on this slide. So we have X is the data, so we transform it into so-called keys and queries, and so the Q and K, when they are multiplied, so because we match all tokens to all tokens, so it becomes square in the number of tokens. Now, idea of this paper is very simple, and surprisingly it works well, is that before we multiply these two matrices, we transpose them. And if you transpose them, well, you can still see it as a attention. I say it's a pairwise interaction, but it's now the size of the output matrix is not n square, it's d square. And this d is the feature dimension, which is fixed, and it's up to you. You can define it as any number. So that's the main trick. The complexity from n square becomes order of n. Why it works, one can speculate, and there are some ideas, explanations in the paper. But the fact is that the complexity becomes n without n square. Okay, I'll just skip these slides, and here what you see that, right? So they particular for images, and it's important for text, but particularly for large images. If you want to analyze large images, then you will have lots and lots of image patches, and making a square out of, say, 10,000 image patches, you get to a large number, and that's why the complexity of standard transformers increases a lot and basically it becomes infeasible for large images, while in our case, we can process large images and with linear complexity. Right, so I have to skip some slides. So here's a just example of what we can do. In the paper, there are results for image net classification, which are pretty state-of-the-art. And in addition, one can show that transformers now can be applied to, say, image segmentation for very large images. So here's a 6,000 by 4,000 image, which can be processed. Some visualization, what this transformer actually learns. The code is online. And I'm finishing. So here's a summary of more or less all papers which I talked about. So they are all online, of course. And not just the papers, but also project, for many of them, project pages, and code is available. So you're welcome to see it on my website. And the very last slide is just advertisement. So as said before, so I'm leading two labs. One is in INRAE Paris. It's a computer vision lab. And another more industrial applications research. So we have a research lab at Vision Labs in Moscow. So if you are interested in some of the topics which I described, so you're welcome to apply. And thank you for listening. So if we have a few minutes for questions, I will be very happy to answer.
Спасибо, Иван. Ну, вообще у нас сейчас перерыв будет, да, получасовой, и, в принципе, мы можем прихватить минут 15 на ответы на вопросы, я думаю, если Иван не против.
Я не против.
Хорошо, ну так, кто готов спросить или кто хочет? Да, есть вопрос. Ага, сейчас микрофон дадим, потому что иначе невозможно услышать.
Здравствуйте, спасибо за интересный доклад. Мой вопрос такой, вот когда вы тренируете два энкодера и делаете свертку, кто обеспечивает и что обеспечивает одинаковую размерность? Потому что свертку сворачивать вектора можно только одинаковой размерности. То есть мы, конечно, можем фиктивно их нужные, но скорее всего это не то, что вы хотите. Да, вот где-то здесь. Нет.
Ну, например, вот здесь?
Да, вот здесь. Когда вы делаете свертку dot product, то размерность энкодера должна быть векторная. Но ясно, что обычно информации в видео гораздо больше, чем информации в тексте. И как бы сжатие, ну, как вы обеспечиваете... Мой вопрос такой, как вы обеспечиваете одинаковость, ну или там ребята, которые это делали, обеспечивают одинаковость размерности с тем, чтобы это было осмысленно. При этом, чтобы эта осмысленность была и в произведении. Спасибо.
Механически, то есть как это работает, просто размерность, она задается тем, кто создает алгоритм. Да, то есть мы просто сказали, что у энкодера F и у энкодера G они должны быть одна и та же размерность, например, 512. Все. То есть это просто задано. Дальше совершенно верно, как вы отметили, что информации в F будет сжата, и, возможно, возможно, вот это 512 значений, возможно, их будет недостаточно для того, чтобы решить проблему. Здесь можно ответа точного нету, достаточного и недостаточного, потому что как это проверить? Может быть, там кто-то изобретет сеть, такую F, что там будет все супер. Но интуиция, кажется, верной, она, в принципе, соответствует тому, что мы делаем здесь, да, то есть вот эти результаты, они как раз и говорят о том, что если мы не уменьшаем репрезентацию картинки до какого-то вектора, а производим какие-то операции до сжатия, производим сравнение с текстом до сжатия. То есть то, что именно происходит внутри трансформера, результаты получаются лучше. То есть это то, что я говорю, это просто подтверждает вашу интуицию, что действительно, если мы просто тренируем сеть на какой-то вектор, результат получается хуже. Дальше, то есть можно Ну, в общем, вот это, что здесь в этой статье происходит, получается, мы пытаемся полечить проблему слева дистилляцией из более хорошего решения справа. Не знаю, то есть как бы ответа полного, наверное, на ваш вопрос просто нету, потому что, ну да, то есть информация, скорее всего, будет теряться, но мы хотим затащить в этот вектор F как можно больше информации. Где предел, неизвестно, может быть, предела нет, может быть, в итоге будет достаточно. И, кстати, вот последние работы, которые, там, клип, если от OpenAI, интересная работа, очень простая сеть, ну, то есть там просто трансформеры берутся, вот именно как здесь слева, но очень-очень много данных, и они показывают, то есть даже лучшие результаты, чем у нас, просто тренируя вот левую модель здесь, dual encoder, на очень большом количестве данных.
Спасибо. Можно уточняющий вопрос? Вот не пробовали ли вы связать, делать дополнительный слой, который преобразует вектор F в вектор G, то есть восстанавливает в каком-то смысле одну по другой? И эта связь тогда у вас будет, как бы, вы будете ее учиться внутри, ну вот как сжимающий автоэнкодер, понимаете, да? То есть мы сначала сжимаем, а потом разжимаем.
Да, мы так делали, я думаю, что точно есть работы, которые... Где-то я видел, сейчас не могу вспомнить точно. Должны быть работы, которые так делают. То, что они не очень как бы, так, выбиваются из общей массы, наверное, говорит о том, что они примерно работают так же, как и здесь. Ну, да, можно действительно придумать там генеративный лосс из F на G, из G на F, плюс еще вот этот similarity loss, как бы все три лосса оптимизировать. Кажется, ну, просто от того, что эти статьи не очень как бы сейчас всплывают в памяти, наверное, они, наверное, работают, но не намного лучше, чем просто такой similarity loss.
Спасибо. Еще вопросы? Да, вот тут рука.
Спасибо за выступление. Мне интересно, вот вы где про дистилляцию было, где улучшали маленькую модель, там, получается, вот результат добились дистилляция плюс ранкинг. А получается, это как бы обучение одновременно происходило, то есть мы дистилляцию и добавляли как добавочный, вот как сам процесс шел от обучения конкретно с дистилляцией и ранкингом.
Ну, ранкинг — это просто постпроцессинг, там обучения никакого вообще нет. Дистилляция, она, как и у Хинтона, сначала тренируется Vision Text Transformer, то есть учитель, да, а потом обучается dual encoder дистилляции, то есть вот путем Kyle divergence, то есть чтобы обучается так, чтобы распределение значений слева и справа в батче были похожи.
А я тогда не понял, как ранкинг конкретно работает? Вот ранкинг можете показать? Да,
ранкинг, да, перескочил. Ну, да, на самом деле все очень просто и стандартно. То есть что происходит? У нас есть быстрая модель, да, быстрая модель — это dual encoder, который просто делает dot product. И мы его запускаем на всех миллионах картинок в базе. Это быстро. Дальше мы берем, скажем, там, самые топовые результаты, которые получились, например, там 100. И, кстати, тут в этой таблице можно посмотреть, там можно брать K10, K10, например.
То есть мы одновременно используем и быструю, и малую сеть, имеется в виду?
Да, то есть мы сначала используем быструю, вот, и потом, то есть мы использовали быструю, получили, например, 100 лучших результатов в каком-то порядке. И дальше запускаем медленную модель только на вот этих 100, потому что там, запустить ее там на миллионе мы не можем, это очень, очень долго. Мы запускаем,
то есть мы как бы отсекаем часть данных быстрой моделью, а потом доулучшаем с медленной, да? Ага.
И это вот именно в инференсе, то есть здесь тренировки никакой нет.
Спасибо.
Так, еще вопросы? Да, вот есть.
Иван, добрый день. Можете чуть поподробнее объяснить последний вот про кросс-корреляцию, по-моему?
Да.
Вот переменная d маленькая, вот это пространство. Что это за пространство?
Это просто пространство.
Латентное какое, да?
Пространство признаков.
Признаков, ага. То есть получается, что оно сильно меньше, чем вот наши входные, а вот порядки...
Да, оно фиксировано, то есть его можно сделать любым, можно там сделать 128 там, или 1000. Но главное, что оно фиксировано.
Главное, что оно фиксированное. Понятно.
То есть можем взять большую картинку или там очень длинное видео и комплекс, ну, не то чтобы, нет, там комплекс там будет расти, но оно будет расти линейно, а не квадратично.
То, что он не зависит от длины последовательности, да, входной?
Да.
Ага, все понятно.
Нет, то есть он зависит линейно. Я стандартный трансформер.
Ну, да.
Квадратичный.
Спасибо.
Так, еще вопросы? Так, вопрос от меня как от ведущего, не могу не удержаться. Скажите, пожалуйста, Иван, а вот вы рассказывали и показывали, да, огромные датасеты, это 100 тысяч часов видео, там новые датасеты у вас по ответам на вопросы, тоже с видео. А если не секрет, какие сервера вы используете для того, чтобы работать с этими датасетами?
Здесь, чтобы обучать сети end-to-end, да, нужны мощности. Если просто обрабатывать видео уже предобычными сетями, что-то с ними делать, здесь там суперкомпьютера не нужно. Здесь будет достаточно, там, не знаю, какого-нибудь сервера, там, не знаю, с 4-8 GPU. Чтобы обучить такую модель, сейчас я точно уже не скажу, потому что это аспиранты наши делали, но там точно нужно, сейчас, чтобы не совсем соврать, в порядке больше, то есть нужно там, 60 и больше GPU иметь и тренировать там несколько дней в таком порядке. Это очень примерно. То есть у меня критерий такой, что чтобы натренировать такую сеть, нам пришлось заслать нашего аспиранта в DeepMind и там.
Спасибо. Так, еще есть вопрос у меня. А скажите, как вы считаете вообще перспективы трансформеров в реал-тайм? Или они будут, так как вы показывали, как-то вспомогательно, гибридно использоваться с быстрыми моделями?
Все очень быстро развивается, это сложно предсказать. Кажется, что одна из, может быть, зацепок и положительных моментов в трансформере в том, что даже если там это квадратичная зависимость, то, в принципе, не обязательно брать полную матрицу. Есть статьи, которые смотрят, сейчас нет хорошей картинки перед глазами, но вот эта матрица А, да, там она размерностью n квадрат, где все токены друг с другом сравниваются. Но кажется, что если знать, какие токены нужно сравнивать, не нужно, то окажется, что те, которые нужно сравнивать, их намного меньше, чем которые нужны. Может быть, как раз здесь даже можно получить быстрее. Конкретная проблема, которую сейчас думаю, это, например, энкодинг для 3 размеров, там, point clouds. То есть point clouds — это что-то такое, это точки, которые в трехмерном пространстве как-то распределены, которые там с Kinect или с какими-то depth-камеры получаются. То есть там большинство, то есть если просто их в трехмерную грид запихивать и делать конволюции поверх этого, 3D-конволюции поверх этого грида, то будет очень неэффективно, потому что большинство пространства, оно пустое. Кажется, например, если трансформер сюда применить и делать pairwise interactions только тех частей, где у нас данные, собственно, есть, то, кажется, будет еще лучше, эффективнее, чем свертки. Я, кстати, такого еще не видел, то, что мы хотим попробовать.
Спасибо. Да, появился еще вопрос.
Спасибо за доклад. Я хотел бы спросить, там, где вы показывали одна архитектура клипа, а другая Vision, трансформер. Вот я хотел спросить, вот если правую архитектуру обучить на меньшем наборе данных, она сможет превзойти клип по качеству?
Ну, наверное, если там, взять, не знаю, 90% данных, наверное, она... То есть как бы здесь будет трейд-офф, конечно. Здесь как бы есть результаты. Да, есть. То есть dual encoder не то, что он, который клип, да, он не то, чтобы он совсем плохо работает, ну, вот в нашем случае. То есть он тоже работает. То есть, понятно, что если уменьшать данные, то вот эта красная часть правая, она будет уменьшаться, в какой-то момент она будет ниже, чем зеленая. Ну, не знаю, может, я неправильно понял вопрос?
Неправильно поняли, спасибо.
Спасибо. Еще вопросы появились вот в первом ряду. Вот здесь, вот.
Иван, у меня еще вопрос. Я просто не очень хорошо в Computer Vision. Все-таки можете сказать, имеет ли смысл вот, обрабатывать картинку целиком, а не обрабатывать ее по частям, в какой-то последовательности? То есть кажется, что это может сильно сократить как раз-таки, ну, увеличить скорость обработки, если мы будем обрабатывать ее какими-то кусочками, ну, грубо говоря, как мы смотрим, да, мы фокусируемся на чем-то одном и постепенно как бы понимая, ну, как бы глядя на части картинки, мы понимаем, как бы, ну, нам есть смысл куда-то еще дальше смотреть и куда. Вот. И, возможно, это будет быстрее, чем, ну, то есть вот сразу обработать всю картинку с квадратичным количеством пикселей и понять, что там 90% этой картинки нам вообще не нужно. То есть она не говорит нам ни о чем. Вот можете что-то по этому поводу сказать вообще, насколько это популярный вообще подход и имеет ли он смысл?
Ну, да, нет, конечно, нет, идея, она существует давно, и, наверное, в принципе, в каком-то виде ее можно разглядеть практически во всех методах. То есть то, что вы говорите, да, там на какую-то часть больше посмотреть, чем другую. Ну, во-первых, чтобы понять, на какую часть смотреть, нужно все равно полную картинку обработать.
Почему?
Ну, потому что если мы что-то совсем, какие-то пиксели вообще не увидели, то мы... Не, ну, контекст, он, конечно, говорит, что можно предсказать по... Ну, собственно, как... Да. То есть можно предсказать по контексту, что находится вот в конкретном месте, но если мы... Все равно контекст тоже нужно.
Не, ну я понимаю, да, про контекст, но тем не менее, то есть, как бы мы... Ну, то есть, грубо говоря, если я смотрю на... сейчас... то есть я не буду искать корову в небе, я буду искать корову на траве, наверное, все-таки. И, то есть,
нет,
я...
вот для того, чтобы понять, что есть небо, что трава, все равно нужно какой-то приправку делать.
Все, я понял. Ладно, спасибо.
Так, еще. У меня есть еще, наверное, уже получается завершающий вопрос. А смотрите, а какие технологии, вот вы работаете фактически частично в РАИИ, да, и в Vision Labs, да, тоже вносите свой вклад вот, в московскую компанию, достаточно известную в сфере распознавания лиц в первую очередь, хотя, может быть, и не только сейчас. Так вот, и вопрос такой, какие технологии научные все-таки удается внедрять, ну, в какое-то такое коммерческое применение, в какую-то реальную практику?
Ну, да, реальная практика, она очень полезна, без нее. То есть можно уйти и писать статьи на темы, которые никому не интересны. То есть как бы такой фидбэк из индустрии очень важен. Он дает правильные и интересные направления, куда делать исследования. В другую сторону, конечно, тоже, то есть здесь там, количество данных и реальные данные, они часто в статьях, которые мы делаем, да, можем там накраулить там, YouTube-видео, но все равно это какие-то более академические данные, то есть вот именно применение к реальным проблемам, их, конечно, лучше делать больше в индустриальной. Если хочется повлиять на мир вот именно с практической точки зрения, чтобы донести технологию людям, то здесь компании лучше. Если я еще могу проще сказать, то есть цель в исследованиях — это в ИНРИ сделать что-то, что работает хотя бы один раз, ты ничего не делал. В компании это сделать так, чтобы вот это, то, что уже один раз заработало, чтобы она работала всегда, везде, и быстро, и приносила пользу.
Спасибо.
Поэтому друг друга дополняют активности.
Спасибо большое. Так, ну, наверное, на этом закончим лекцию. Поблагодарим Ивана. Так, ну
Спасибо.
да, спасибо. Ну что, и у нас 10-минутный где-то перерыв, и после него у нас будет лекция Алексея Евгеньевича Осадчева, который расскажет про декодирование, интерпретацию кортикальных сигналов с компактными сверточными нейронными сетями.
Взять шарик?
Нормально себя чувствуете?
Угу. Класс.